Sorry, yeah, we are recording. Welcome everyone to the 125th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Shubhodip Mondal from the University of British Columbia, and he will be talking to us about unipotent homotopy groups of Calabi Yau varieties.
All right. I'd like to thank you very much for the invitation to give this talk and also for the introduction. So I'll be talking about unipotent homotopy groups of Calabi Yau varieties, and everything I'm talking about is joint work with Emanuel Reinecke. And this is also all in our paper, which is called Unipotent Homotopy Theory of Schemes. So let me start by just briefly mentioning what are the main goals for this talk today. So at first, I will give you the notion of unipotent homotopy type, which will also lead to the definition of unipotent homotopy group schemes, which we denote as phi n u of x for the nth one of any algebraic variety x. And this will also use some derived algebraic geometry that we will see very soon. And then I would also talk about some properties and relationship with some more classical notions, namely, I think Nori's work on fundamental group scheme, as well as Artin and Mazur's work on étale homotopy types. And after that, I want to focus more today on these unipotent homotopy group schemes in the context of Calabi Yau varieties. And I will explain why they are derived invariants for them. And when we get there, I'll also kind of explain maybe the meaning of some of these words. So this would be the main goals. And so feel free to ask any questions or anything during the talk as well. Okay, so to define unipotent homotopy group schemes, so just first quickly need to recall the definition of affine stacks, which is due to n. So let K be a field, and Fk will be the category of affine schemes over K. So these are just ordinary affine schemes. And we will let S denote the infinity category of spaces, and which is also nowadays sometimes called anima. So a functor from the opposite category of affine schemes over K to S may be called a higher pre-stack over K. And in particular, if they satisfy some kind of sheafiness, then we will call them higher stacks. So maybe I should point out that, so I think in the usual theory of stacks, we are actually interested in functors that take values in groupoids. And so these groupoids can be thought of as one truncated spaces, but in the notion of higher stacks, we want to land in the infinity category of spaces without making any kind of one truncatedness assumption. So let me now talk about the notion of when is the highest pre-stack an affine stack, and this is due to n. So a higher pre-stack, which is a functor x from the category of affine schemes to spaces, is called an affine stack if it is representable by a cosimplicial ring R, which is to say that x of spec p as a functor should be isomorphic to the mapping space computed in the category of cosimplicial rings, which should be thought of as an infinity category from R to B. And so because this mapping space is being taken in an infinity category, this is kind of naturally a space or an anima. So in the usual theory of affine schemes, I could have started with some functor x from the opposite category of affine schemes to sets instead of spaces. And this would have been called an affine scheme if it was representable by an ordinary ring R. So for affine stacks, we change from ordinary rings to cosimplicial rings. And the functors are also kind of taking values in spaces. So an affine stack is going to be a more general notion than that of an affine scheme. And we'll be seeing some examples very soon as well. Yeah, so now let me also remark that here I was using the infinity category of cosimplicial rings, but one can also replace this by what's called the infinity category of derived commutative rings and still be able to get the same notion. And actually, by using derived rings, one can also get a relative notion of affine stacks. So, so I think one can also make a notion of when is a map between two higher priest stacks relatively an affine stack. And so this is joint work with Akhil Matthew. And for the purpose of this talk, this will not really be very important. But I just wanted to mention that one can replace cosimplicial rings by the category of derived commutative rings as well. Okay, so let's see some examples now. So as I was mentioning, we could take R to be an ordinary ring or maybe a discrete cosimplicial ring. And then we'll recover the notion of affine schemes. So every affine scheme will be an affine stack. And so somewhat more surprisingly, every quasi-affine scheme is also an affine stack.
Video is not turned on.
So for example, I could take A2, the affine plane, and then remove the origin. So that's not an affine scheme, but it's quasi-affine, and it would still be an affine stack. So let me just mention an example of being relatively affine, which can capture really a lot of examples. So Pn, the nth projective space, will be an affine stack over BGM, where BGM is the classifying stack of the multiplicative group scheme GM. And so this stacks KGA comma N, which is kind of an analog of the Eilenberg-MacLane spaces in topology. So they are all examples of affine stacks for all n greater or equal to 0. So let me just say that when n is equal to 1, KGA comma 1 is nothing other than just the classifying stack, which we denote as BGA. And say for KGA comma 2, it can be thought of as applying the classifying stack construction to BGA. So it's B of BGA or B to GA. It's the same thing as what we're calling KGA comma N. The important property of these stacks is that, so I think like the property is very similar to what we see for Eilenberg-MacLane spaces as well. So for example, this stack KGA comma N will only have one non-trivial homotopy sheaves, which will be the pi n. So for KGA comma N, pi n will be isomorphic to GA as a group scheme. And all the other homotopy groups or sheaf of homotopy groups, which is the right notion here, will be just 0.
Shubhodip, I have a question. So you defined in your second bullet point under example, you say that you have this example that any quasi-affine scheme is an affine stack. Can one have a relative version of this sentence? For example, is there such a thing as a relative affine scheme? And can then one say that a quasi-relative affine scheme is a relative affine stack? Or does this not make sense?
I think if you make the notions in the appropriate way, maybe one can make a statement like this. Yeah.
Okay.
Yes, actually, the reason why Pn is an affine stack over BGM is actually because Pn is in some sense quasi-affine over BGM, because we can take the n plus first affine space, and then that is affine and has a grading, so it has a GM action. And then you remove the origin from there. So then you're making it quasi-affine. And then you quotient by GM. So it's in some sense, I think it's quasi-affine over BGM. And that's actually exactly the reason why it's an affine stack over BGM. Yeah.
Thank you.
Yeah. So let me give some non-examples. So there's stacks KGM comma N are not going to be an affine stack for any n greater than 0. So GM will be an affine stack because GM is an affine scheme, but already starting from BGM, B2GM, these are not going to be examples of affine stacks. Okay, so let me now talk about the notion of unipotent homotopy type. So let X be a scheme over K, and we could also replace X to be any stack or a higher pre-stack, let's say, but we'll focus on schemes for now. So let U of X be the affine stack that is universal with respect to receiving a map from X. So this is universal with respect to having a map X to U of X. So I guess to spell it out, if I have any affine stack Y and then the map from X to Y, then it must uniquely factor through X to U of X. So one can define U of X by this universal property, and this will be called the unipotent homotopy type of X. So this by definition is an affine stack, which is so a higher pre-stack, let's say. So now let X comma little x be a pointed connected scheme. So this little x is supposed to be a k-rational point of the scheme X. And so now, just as for spaces, if we have a point, we can take homotopy groups. For stacks, one can take homotopy group schemes. So we can take pi I of u of x. So I think we define it to be pi I of u of x, and the homotopy kind of group schemes are being taken with respect to this point little x. But so I think a priori this pi I u of x, as you have defined, will only be a sheaf of groups. It will be some sheaves defined from the opposite category of affine schemes to just ordinary groups. But then in this case, actually, this is representable by an affine unipotent group scheme over K. This representability also comes from Toen's work. So the objects we are defining, this pi I u of x, a posteriori, these are very concrete objects. These are some affine group schemes, and in particular, they're also unipotent. And we will call this the ith unipotent homotopy group scheme of X. So let me just give a very sort of quick reminder on what being unipotent means. So recall that an affine group scheme G is called unipotent if for every non-zero representation V, we have a non-zero fixed vector, which is to say that V to the G is not equal to 0 whenever V is not equal to 0. And let me also point out that we don't assume any kind of finiteness conditions on G. So G is allowed to be of infinite type. For example, an infinite product of unipotent group schemes will also be unipotent in our sense. And I think the unipotent homotopy group schemes that we have defined, usually they are not finite type. So usually they're also infinite type. So let me give some examples. So examples of unipotent group schemes include GA, the additive group scheme, which is the natural group structure on the affine line. And in characteristic P, actually, there are many interesting examples of unipotent group schemes. For example, you could take Z mod P, view it as a discrete group schemes. And you could also take alpha P, which is the kernel of Frobenius on GA, which only exists in characteristic P and is an example of unipotent group scheme. GM, on the other hand, the multiplicative group scheme, is not unipotent group scheme. And in characteristic P, if you take mu P, which is the kernel of Frobenius on GM, that's not a unipotent group scheme. And neither are this Z mod L's for any prime L not equal to P. So all of them are not examples of unipotent group schemes. They're actually all multiplicative. Okay, so let me now talk about some of the basic properties of unipotent homotopy group schemes and explain how they kind of relate to some of the more classical invariants, which is what I was mentioning is one of our goals. So let x comma little x be a pointed scheme of finite type over a field K, such that H0 of x comma over I think the global sections are just isomorphic to K. So this is some kind of a notion of being cohomologically connected. So so here we have a natural isomorphism of pi1 u of x, which is the first unipotent homotopy group scheme. And that's isomorphic to the right-hand side, where right-hand side denotes the unipotent fundamental group scheme constructed by Nori. So we'll not really get into the details of Nori's work, but let me just say that the construction that Nori gave was completely different, and it kind of uses some kind of a some categorical framework. But our construction instead is based on derived algebraic geometry, the notion of affine stacks, as we saw. So this also gives a very different way of defining the unipotent Nori fundamental group scheme. By using our approach, we could also define the higher versions of Nori's unipotent fundamental group schemes that we would not have gotten by using the classical approach of Nori. So let me kind of mention another result to show how they will connect with some other classical invariants. So for here, the setup would be that X is a proper cohomologically connected pointed scheme over an algebraically closed field of characteristic P. So then for all I, so I could take the reduced part of this pi u of x. So this pi u of x is some unipotent group scheme, and I could take this closed reduced subscheme, which is again a group scheme. So I'm calling the reduced part of it. So that would be isomorphic to the pro P part of the ith Artin Mazur Ital homotopy groups. So this Artin, Artin and Mazur had defined this notion of Ital homotopy types, and which also leads to Ital homotopy groups, which can be seen as a generalization of Grothendieck's notion of the Ital fundamental group, which gives the pi 1, and Artin and Mazur had extended it to be able to get higher Ital homotopy groups as well. And so let me also point out that the construction of Ital homotopy groups is quite different. And in the language of, I think, Toen-Vizorsi and Lurie, it uses the shape of the Ital topos of the scheme X. But then, as I was saying, our approach was based on affine stacks. And to prove this comparison result between the reduced part of unipotent homotopy group schemes and the pro-P part of the Artin Mazur Ital homotopy groups, so it kind of really uses the work of Chris, Goes, and Mandel on p-adic homotopy theory. So before we move on, let me just give a quick summary of maybe some of the takeaways, which is that, yes, as we see, this unipotent homotopy group schemes are certain new invariants that we can attach to any algebraic variety X using Toen's theory of affine stacks. And so actually the unipotent homotopy type, so it's possible to spell out kind of what kind of information it captures. So the information is about some kind of a derived commutative ring structure of R gamma X comma O, which is the cohomology of X, but not just as a complex, but we want to remember some more deeper and more rich structure, which is that of this derived commutative ring structure. So this, in some sense, is very similar to what happens in, say, rational or p-adic homotopy theory, where we try to study a topological space Y in terms of, say, some kind of algebra structure, sometimes maybe co-simplicial ring structure, sometimes E-infinity algebra structure, on the singular kind of quotients, C star y comma k. And so for I equal to 1, our unipotent homotopy group schemes, as we said, it's related to Nori's work on fundamental group schemes. And for a general I, the unipotent homotopy group schemes, they relate in a very precise way to Artin and Mazur's work on Ital homotopy theory. And actually, in the p-adic context, the unipotent homotopy group schemes, they have more information than the pro-p part of the Ital homotopy group. So it sees some more nilpotent information that would not be seen in Ital homotopy theory. And so this unipotent homotopy group schemes are also related to certain formal groups constructed by Artin and Mazur, and we will come back to this later. So I think this will play a very important role when we talk about Calabi Yau varieties, for example. So everything I'm talking about is in some sense unstable homotopy theory, but one can also develop a notion of stable homotopy theory in this unipotent setup. And this is part of my joint ongoing work with Tassos Morinos and Lucy Yan. So I just want to mention that as a aside.
Can I ask a question?
Yeah, sure.
So you mentioned earlier when you were talking about how your approach differs from the classical approach of Nori. And here also, here you're saying in the I equals 1 case, you guys get back what, like the construction for the unipotent fundamental group scheme. So, I mean, of course, I mean, you mentioned this also, like in the Nori approach, there was the Tanakian formalism stuff. So in the DAG approach, there is none of it, or is there some of it in a different, like, you know, in a generalized version?
Yeah, actually, so the way we are doing it, at least a priori, they're very different. But then maybe if you try to understand, then like, I think when you're trying to prove it, you'd see there are some similarities, but yes, actually, really, in the approach using derived algebraic geometry, you're also able to make sense of the higher homotopy group schemes, which in the Nori approach is very difficult to do.
I see, that's right.
Because I think in that approach, you are trying to understand when is some category rep G for some group scheme G. And then that group scheme G is kind of like only the pi 1, and you don't really see higher homotopy groups this way. Yeah.
Okay, thank you.
Okay, so now let me kind of move towards the question of derived invariance for Calabi Yau varieties that I wanted to talk about today. So the basic question that we're interested in is, say, for what class of smooth projective varieties X and Y defined over, say, an algebraically closed field K that we may assume to be of characteristic P, does X and Y being derived equivalent imply that there is an isomorphism of unipotent homotopy types, Ux and U of Y? So this is a very kind of general question that one can ask for basically any invariants that we define for varieties or schemes that are the derived invariants. And so in particular, we are interested in the same question for the unipotent homotopy type. And so let me just say that we say that X and Y are derived equivalent if there is an equivalence of the bounded derived category of covariant sheaves on X and Y as k-linear triangulated categories. And so if either X or Y have an ample canonical or anti-canonical bundle, which is to say omega X is ample or the inverse of omega X is ample, then X and Y being derived equivalent would actually imply, by a result of Mondal and Orlov, that X is isomorphic to Y. So then, of course, if X and Y were isomorphic, then certainly the unipotent homotopy types will also be isomorphic. So our question would have a positive answer in that case, directly coming from the work of Mondal and Orlov. However, I want to give an example later on to, well, at least mention that the question will not always have a positive answer. So say if you have an abelian variety A, then its dual abelian variety A dual are always derived equivalent. And this is due to work of Mukai, but they will not always be isomorphic for higher dimensional abelian varieties. So that already gives an example of two varieties which are derived equivalent, but they don't have to be isomorphic. So that already happens for abelian varieties. And the canonical of the abelian variety will be trivial. So it will not be ample or anti-ample. And so in our work, we also gave examples of some abelian threefolds A such that pi1 u of A and pi1 u of A dual are not isomorphic. So if the homotopy group schemes are not isomorphic, then the homotopy types can't be isomorphic either. So the question that we asked above can't always have positive answers, because A and A dual will be derived equivalent, but the unipotent homotopy types will not be isomorphic. And so let me also say that we don't actually have any counterexamples for, I think, when the dimension is less than or equal to 2, at least when the characteristic is not equal to 2. But so the first time we would see some counterexample will be at least for threefolds. Okay. So what's the strategy for finding such an example? Maybe I'll outline the strategy very generally. So for any abelian variety A, it's actually possible to compute pi1 u of A in somewhat explicit terms. That doesn't say anything about unipotent homotopy, and it's very concrete. So this pi1 u of A is in some sense Cartier dual to a formal group obtained by completing the dual abelian variety A dual at 0. So this A dual is an abelian variety. So it's also smooth in particular. And so if I take the formal completion of any smooth group scheme at the origin, then the group structure would restrict to the infinitesimal neighborhood at 0. So in particular, it would kind of induce some group structure on formal affine space. And that's exactly what we call a formal group. So by doing this construction, whenever we have a smooth affine group scheme, or say a smooth group scheme, we can complete at 0 to define some formal group. So we could do that for the dual abelian variety A dual, and that would recover the fundamental, so I guess the first unipotent homotopy group scheme of A. And so now these formal groups, they can be understood in terms of p-divisible groups associated to abelian varieties. And so these are very kind of well-studied objects that would allow us to connect them to a lot of classical work and classical theories. And in particular, from these p-divisible groups, by using work of Wood, we can construct certain abelian varieties, which would ultimately allow us to find this kind of examples. So one of the things that we see is that this pi1 EU of A, the first unipotent homotopy group scheme, is related to some kind of formal groups. And this is something we will come back to later on as well for Calabi Yau varieties. Okay, so now we will move to, I think, Calabi Yau varieties, and we will be interested in the question we asked before, which was this question, in the context of Calabi Yau varieties. So for us, a Calabi Yau will mean a smooth proper variety X of dimension n such that cohomology of the structure shift vanishes in degrees in between, strictly in between 0 and the dimension. And more importantly, I think the canonical is trivial. So from these conditions, by said duality, it would follow that dimension of h and x comma o as a k-vector space is also equal to 1. This to be isomorphic to h0 x comma o. So in dimension 1, these Calabi Yau varieties are called elliptic curves, and in dimension 2, they're called K3 surfaces. So when we try to understand the previous question for Calabi Yaus, we'd see that so the answer is actually quite different from what we see for higher dimensional abelian varieties, where the answer is that it can be false. But for Calabi Yaus, the answer is actually affirmative. So if you take two derived equivalent Calabi Yaus x and y over some algebraically closed field of characteristic P, then we actually have an isomorphism of the unipotent homotopy types of x with the unipotent homotopy types of y. So the answer is positive in this case. And in particular, this means that the unipotent homotopy group schemes pi iu of y, x and pi iu of y are also isomorphic for all I greater or equal to 0. So the unipotent homotopy group schemes are also derived invariants for Calabi Yaus. So in what follows, I will try to explain some of the key steps in the proof of this result. So let's at first maybe focus on proving the isomorphism of the unipotent homotopy groups for every I. So as long as I is less than n, there is some kind of Revich theorem that one can obtain in the unipotent homotopy case, we should say that because this cohomology groups for the Calabi Yau was 0 between 0 and n, the homotopy groups, the unipotent homotopy groups are also trivial for I less than n. So as long as I is less than n, both sides are 0. So then they're definitely isomorphic. But in particular, the result that we aim to prove, it also says that the nth homotopy, the nth unipotent homotopy group schemes are also isomorphic. And so that one is not 0. And the fact that they're isomorphic is closely kind of related to a result of Antiu and Bragg, as we'll see very soon. So this pi nu of x being isomorphic to pi nu of y is kind of the very first interesting case. And so this is what I'll be explaining in the next slide. So this is kind of obtained by first proving a way to recover Artin Mazur formal groups from unipotent homotopy group schemes. So now I'll give the definition of Artin Mazur formal groups in the context of Calabi Yau varieties. But I should point out that this work of Artin Mazur, it I think works much more generally than X being a Calabi Yau. So it can be made sense of for any variety X. Sometimes the formal groups that they define, they might not be representable. So the formal groups might not be well defined, but a large part of the work of Artin and Mazur actually works for any for I think any algebraic variety X. But since you're already interested in Calabi Yaus for now, I'll also specialize this definition for Calabi Yaus. So let X be a Calabi Yau variety of dimension n. So then Artin and Mazur, they first construct certain functors, let's call it phi n of x, from the, I think from the category of Artinian local rings over K to the category AB of abelian groups. And the functor is defined in the following manner. So we take some Artinian local K algebra S, and we send it to the kernel of this induced map on Ital cohomology of GM. So the source of this map is the Ital cohomology of X base changed to S with coefficient in GM. And then the target of this map is the nth Ital cohomology of X with coefficient in GM. So in their paper, they also kind of call this a deformation of Ital cohomology of GM. And they use the term deformation cohomology of GM for this kind of functor. So here we have this functor from Artinian local case schemes to the category of abelian groups. And they prove that in this situation, for example, because of the cohomology vanishings that are available for Calabi Yau varieties, this will be representable by a one-dimensional formal group over K. So by definition, one-dimensional formal group would mean a group structure on the formal affine line. And so this phi n X will be called the Artin Mazur formal group of X in this context. So here, this n is actually equal to the dimension of the Calabi Yau n. Although it's not at all necessary to define this kind of functor. The functor could be defined for any value of n. Does not have to be the dimension. But here we're specializing to the case when this Hn, the n stands for the dimension. So in general, this kind of formal groups, they can be classified by their Dieudonné modules, which is some kind of linear algebraic data that would not really spell out in detail. But let me just mention through examples that the Dieudonné module of the Artin Mazur formal group, it can be expressed completely geometrically as an invariant of X. And this is given by Hn of X, comma W of Ox, where the latter denotes Serre's with vector cohomology. And this has some natural operators, F and V, that satisfies some identities like Fv equals P, Vf equals P, etc. So the exact definition of Dieudonné modules will not really be important for us. And what would really be important later on is that kind of the data of the formal group phi n of X is equivalent to the knowledge of this cohomology group Hn X, comma W omega of W O of X with these operators. And so let me also say that says with vector cohomology. So here we're using with vectors. So this with vector is a construction that can be applied to any ring, and the output would be another ring. And in particular, because it's a functor, it can be also applied to any sheaf of rings, such as OX. And this W of X means that we're applying the with vector construction to the sheaf of rings OX. And then we can take its cohomology. So let me also state our result here, which would allow us to reconstruct the Artin Mazur formal group from unipotent homotopy group schemes. So for X as above, which is a Calabi Yau of dimension n, we show that the nth unipotent homotopy group scheme is dual to some one-dimensional formal group. And moreover, that formal group is canonically isomorphic to the Artin Mazur formal group, phi n of X. So the unipotent homotopy group scheme pi n u of X can be understood in terms of the Artin Mazur formal group. And also conversely, the Artin Mazur formal group could be understood in terms of the unipotent homotopy group scheme pi n u of X. And this is something that will play a role in our work later on. So we're interested in explaining why pi n u of X is isomorphic to pi n u of Y for two derived equivalent Calabi Yau varieties, X and Y of dimension n. So this actually uses the notion of topological restriction homology, or TR, and this is the part that was used in the work of Antio and Bragg, which is what I'm explaining now. So for every smooth proper scheme X, one can define its topological restriction homology, TR of X, and this is a construction of Hesselholt, and this is some kind of a spectrum, which can be kind of thought of as some more topological variant of the notion of a chain complex. In particular, one can take homotopy groups of this TR of X, just as we can take homology or cohomology groups of chain complexes. But by definition, this TR of X, Yeah, so here by definition, this TR of X only depends on the category of perfect complexes on X. And therefore, just by definition, this will be a derived invariant. So if we have any two varieties X and Y, which are derived equivalent, their TRs will be isomorphic, just by definition. And so this is what Antio and Bragg proved, which is kind of a recent result. So let X be a Calabi Yau of dimension n. So they proved that the nth with vector cohomology of X can be expressed as the negative nth homotopy group of the spectrum TR of X. So the operators F and V that are defined on the left-hand side, they also make sense for TR, and they also appear in the right-hand side, and this isomorphism is also compatible with the F and Vs. So let me kind of mention the main idea for their proof. So the spectrum TR of X, again, this comes from the work of Hesselholt. So this has a canonical filtration, which is called the motivic filtration. And the graded pieces of this filtration are given by cohomology of this derived forms W omega I of X, which appears in the work of Illuzi. So although this TR of X is always a derived invariant, the motivic filtration in general is not some derived invariant. So it's not really true in general that if you pass through the graded pieces, you'd get some derived invariance. It would be false. But in this case, Antio and Bragg proved that actually you can study this filtration, and the filtration gives rise to some spectral sequence. And then by further analyzing the spectral sequence, they obtained the above isomorphism, which expresses the with vector cohomology kind of directly in terms of TR. So this has some upshots. So it says that, say, in our context of the Calabi Yau variety of dimension n, it says that H and X, W O X will be a derived invariant because it happens to be obtained directly from TR of X, which is a derived invariant. Further, the Artin Mazur formal group phi n of X must be a derived invariant because the Dieudonné module of the Artin Mazur formal group is exactly isomorphic to H and X, W omega X. H and X, W of X. And if that one is a derived invariant, then so is the Artin Mazur formal group. And further, by the result, we mentioned that pi and u of X and the Artin Mazur formal groups are in some sense dual from each other. It would also imply that the unipotent homotopy group scheme pi and u of X is a derived invariant. So this actually proves that pi and u of X is isomorphic to pi and u of Y for two derived equivalent Calabi Yaus X and Y, which is one of the things that we wanted to explain. So in summary, we have proven so far that for a Calabi Yau X, the group schemes, the unipotent homotopy group schemes pi I u of X are derived invariants for I less than equal to n. So now, of course, we need to understand what happens for I greater than n, because we aim to prove that there are derived invariants in general for I greater than n as well. And so more generally, how can we prove that the unipotent homotopy type u of X is a derived invariant, which would in particular imply that all the unipotent homotopy group schemes are derived invariants. So for this, we would use the notion of formal spheres, which is the title of the slide as well. And so the definition we're going to give, it was inspired by the notion of formal circle by Molinos, Roballo, and Toen from their paper called Universal HKR Theorem. So let me give the definition. So let E be a one-dimensional formal group, some arbitrary one-dimensional formal group. And then we can consider the dual of E, which would be well defined as a unipotent affine group scheme, E dual. It will also be commutative. And so now we can take the classifying stack of this group scheme that we call B of E dual, and this will naturally be a pointed connected stack. So we define the formal n-sphere Sn sub E to be the n-1-fold suspension of the classifying stack B of E dual. And so this will again naturally be a pointed connected stack by construction, and we'll call this the formal n-sphere. So let me explain a little bit about why we're calling it the formal n-sphere and why we're defining it this way by analogy with the usual spheres. So if I replace the group scheme E dual just by the ordinary group of integers Z, then BZ, which would be the classifying space of integers, that's just the circle S1. And if we take suspension of the circle n-1 times, then we get something that's homotopy equivalent to the nth sphere Sn. And the construction we are giving here for the formal sphere kind of closely gives some parallel of what happens for usual n-spheres. So now we'll come back to the unipotent homotopy of Calabi Yau varieties. So let X be a Calabi Yau variety of dimension n over an algebraically closed field K of characteristic P. So then we prove that the unipotent homotopy type of X is isomorphic to the unipotent homotopy type of some formal n-sphere, where the formal group E that we saw before is now replaced by this very specific formal group, which is the Artin Mazur formal group of X. So this is the statement that the unipotent homotopy types of the Calabi Yau variety is the same as the unipotent homotopy type of some formal n-sphere. And I mean, I should also point out that certainly X and the formal n-sphere are not isomorphic, but they become isomorphic only after taking the unipotent homotopy type. And so in what follows now, I'll explain the main ideas for constructing just a map between the two. So it would actually be enough to construct a map from the formal n-sphere to U of X, because U of X is by definition an affine stack, and by universal property of unipotent homotopy types, any such map will give rise to a unique map from the unipotent homotopy type of the n-sphere, unipotent homotopy type of the formal n-sphere to U of X. So it would be enough to construct a map from the formal n-sphere to U of X. So note that we have a natural map obtained by composing the arrows that I've written down. So let's go over them. So first we have the formal n-sphere, and that has a natural map to its n truncation. And one can prove for this kind of formal n-sphere, as we have defined, that it doesn't have any homotopy groups in I think degrees less than n, and the nth homotopy group is exactly isomorphic to pi in U of X. So therefore, the n truncation of the formal n-sphere will be isomorphic to this Eilenberg-MacLane stack k pi in U of X, n. But then, if we were to look at U of X, as we said by Hurewicz theorem, U of X also doesn't have any homotopy groups in degrees less than n, and the nth homotopy group directly by definition is isomorphic to pi in U of X, n. And so therefore, we have an isomorphism in the right-hand side as well. And then we can compose to get a map. But the middle isomorphism here, when we said that the nth homotopy group of the formal end sphere is isomorphic to pi and u. This is actually using our definition as well as the fact that the dual of the Artin Mazur formal group is isomorphic to the nth unipotent homotopy group scheme of the Calabi Yau. So if we compose, we get a map from the formal end sphere to the end truncation of ux. But we are interested in constructing a map from the formal end sphere to u of x. So in order to construct such a map, as in one here, now the strategy is to sort of climb along the Postnikov tower. So that in the next slide. So here we have this diagram. So on the right-hand side, we have this maps from the n plus first truncation of u of x to the n truncation of u of x, and from n plus second truncation of u of x to n plus first truncation of u of x, and so on. So the vertical maps on the right-hand side is what I'm calling the Postnikov tower. And we have already constructed a map, which is the horizontal map here, from the nth formal sphere, from the formal end sphere to the end truncation of the affine stack u of x. Now we would like to lift this map stepwise. So in the first step, we want to lift it from a map from Sn to the n plus first truncation. And once we have such a lift, we want to further lift that to the n plus second truncation, and then so on and on. And then we can take a limit to be able to construct a map from the formal end sphere to u of x. So this is what I was calling climbing along the Postnikov tower. But so actually these maps from the n plus first truncation of u of x to the n truncation, they're also kind of well understood. So if you take the fiber over a point, you'd get something like k pi n plus 1 comma n plus 1, which would be some Eilenberg-MacLane stack. So like the fibers of each of these vertical maps, they are very well understood. And therefore, so I think it takes some work, but we could actually very concretely try to understand what are the obstructions to this kind of subsequent lifting from, say, the nth step to n plus first step, and then n plus first step to n plus second step. It's possible to get a very good obstruction theory, which would prove that this obstruction should all lie in some groups of this form. So this is the R plus third cohomology of b pi and u of x with coefficient in this group scheme pi of n plus r plus 1 of u of x for every r greater or equal to 0. So here, by writing it this way, I mean that when r is 0, then this is the group that's relevant to lift from tau less than or equal to n to tau less than or equal to n plus 1. When r is equal to 1, then that's the group that's relevant to lift from n plus 1 to n plus 2. And then when r is 2, that's the relevant one to lift from n plus 2 to n plus 3, and so on. But somehow the good news is that one can prove that all of these groups would vanish. And so for this vanishing, we actually crucially use all the kind of the specifics that are there in our setup. So we crucially use that this pi and r plus 1 of u of x is actually a unipotent group scheme. And that plays an important role in the vanishing. But we also use that the space we're working on, this b pi and u of x, this pi and u is dual to some one-dimensional formal group. So kind of using all of these facts together, we can prove that these groups all vanish. So in particular, there is no obstruction to sort of subsequent liftings. And this would construct the desired map for us. So we would be able to get the map from Sn of phi n of x to u of x. And once we have the map, one can do some work to check that it's an isomorphism. So that's roughly the idea here. So in conclusion, we can prove that u of x is isomorphic to the unipotent homotopy type of the formal end sphere, but the formal group is the one coming from the Artin Mazur formal group. But once we prove that, we also prove that the unipotent homotopy type of X is a derived invariant, because by using this topological restriction homology from the work of Antio and Bragg, we can already say that the Artin Mazur formal group is a derived invariant, and therefore anything that depends on that will also be a derived invariant. And therefore, we get the theorem that we wanted to prove, which is that if X and Y are to derive equivalent Calabi Yau varieties over an algebraically closed field of characteristic P, then the unipotent homotopy types of X and Y are isomorphic, and in particular, the unipotent homotopy group schemes are also isomorphic for every I. Okay. I think this is all I wanted to say, so thank you very much for your attention.
Thank you, Shubhodip. Can we all unmute ourselves and give the speaker a round of applause? If you have any questions, please ask them.
Yeah, I'd like to ask if you can say something more about the stable version of the unipotent homotopy theory that you referred to at the start.
Yeah, so I think this is some ongoing work, and I hope that will appear very soon. But I think the main idea is just that we can also make sense of a notion of spectra in the unipotent setup. So the idea of defining the spectra, which I think in our work, which is ongoing, so we call this unipotent spectra. So what we do, we take the stabilization of the category of affine stacks. And then we get some notion of spectra, which we call unipotent spectra, and then that can be used. So for every scheme, you also have some universal object that you can define, which is now a spectra instead of an affine stack. And then you can also take homotopy groups of that, and that would give the stable homotopy groups. Yeah. Yes, so I hope the work will appear very soon. So then there should be more details available.
Okay. And so do you expect that the unipotent stable homotopy type remembers less or more? Like, would it always be derived invariant or something?
So the stable homotopy type, I think it will be just also defined by the stabilization of the homotopy type. So then I think it would be derived invariant for Calabi Yaus, of course, but in general, I haven't thought about it. Yeah, I think you could ask this question for general algebraic varieties again. What happens for the stable homotopy types? That one I haven't thought about it, but I think it's a good question. I think what's definitely true is that if the unipotent homotopy type is a derived invariant, then the stable homotopy type will also be a derived invariant, but it could go the other way around. That one is a derived invariant without the unipotent homotopy type being derived invariant.
Thank you, Lucas.
Yeah, thank you for the question.
Any other questions? I think you mentioned at some point during the talk as to like for what X and Y do we know that derived equivalence implies UX and UI are the same?
Yeah.
So what's the state of the art on that?
Well, so I guess so far, I think I mean, you get a lot of cases, I guess, from the work of Mondal and Olaf. And then we proved that for abelian varieties, it can be false. And for Calabi Yaus, it's true. I think as far as I know, that's all. It would be interesting to kind of study this in other cases as well.
Okay. Okay.
Yeah.
I was just wondering if the paper by Antio and Bragg had something had made any contributions.
Yeah, right. I think Antio and Bragg, they also studied it for some more surfaces. I think we haven't studied it for surfaces yet. I think it would be interesting to do so. For curves, I think derived equivalent is always isomorphic, so then there isn't much going on. But for surfaces, I think Antu and Brad, they actually did study some of this stuff for surfaces, but our question we haven't studied for surface in general. By what I said, it's true for K3 surfaces, but other than that, I don't know. No, that's a good question. Yeah.
Thank you. Any other questions?
I have a first question. Can you hear me?
Yeah. I can hear you.
Yeah. I'm not familiar with the definition of the highest state. You mean you could view as the Ellenberger-McLaurin space with a group with the additive formal group. Think it as a higher state. You mean the higher state could be represented by a co-simplicial ring R. What's the co-simplicial ring R for the Ellenberger-McLaurin space with a group additive formal group?
You're saying what's the co-simplicial ring
Yeah,
for
you
which
need
would
some
correspond to this
examples.
affine
The
stack?
first,
Yeah.
What's the
So this is a very good question. Yeah. So I think this is what's called the free co-simplicial ring in homological degree minus n. So it's often written as LSIM of k in like I think degree minus n. So I think if you see the paper of Toen, he actually describes that ring. So I think it's like
okay,
yeah.
fine. I will read the
Yeah, so you have to take some of this like free cost. So yeah, I guess I can say it's some free co-simplicial ring in some sense. So the analogy is that if you take n equal to 0, then you're asking this about just GA, and then it's just the polynomial ring in one variable, k of x. But for KGAN, it's also the polynomial ring, but you want to take it on a generator in a homological degree minus n. So it's a little bit different, but it's some kind of a polynomial ring again. Yeah, but this appears in Toen's paper, and I think he explicitly writes down the co-simplicial ring as well. So that is a good place to look.
Yeah.
Thank you, Yan. Any other questions? Anybody? Just I wanted to clarify something. So TRX, the construction depends on the category of perfect complexes, right? So TRX and TRY are the same if and only if X and Y are derived equivalent.
Yeah, so I'm not sure about if and only if, but if X and Y are derived equivalent, then
that is clear. But the other way, is that also true? I mean, if it's only depending on perfect complexes, do I get a triangle equivalence between perfects and perf Y from TRX, TRY being same?
So I think in general, maybe I would expect this to be not true. I mean, I think you're saying that you don't lose any information by passing to TR, which feels a little bit strong.
Okay.
But I could be wrong. Yeah. So
maybe I misunderstood what you meant when you said that as per Hasselhoff's construction, it depends only on perfect complexes, or it is made.
Oh, yeah. So I think maybe then I should clarify that part. So to define TR of X, so first, so this TR of X will be defined directly in terms of THH of X. And then THH of X, it's some construction that you just do to dperf of X, which is the category of perfect complexes.
Sorry, sorry, stupid question. Yeah, of course you will lose something maybe. Okay, sorry. Yeah, it depends on, it's not entirely determined by.
Yeah, right. Yeah. So I think I guess as you said, it depends on it, but it's not necessarily determined by it. So yeah, right.
Sorry. Yeah. Any other questions, anybody?
Yeah, maybe I have one more question then. It's a bit
please.
maybe
Yeah,
more
sure.
technical. I was wondering if so whether this notion of affineness, say for like over derived algebras, whether this is related to the derived category being monadic over, say, some base. So in general, like instead you can ask, if you have a map X to Y, you can ask whether the derived category of X is monadic over the derived category of Y, and this gives us sort of, I guess, one affineness. And can you relate this to the notion of affineness you're using? Is there an implication?
Yeah, so I think for a map like, as you said, from X to Y, I think we could take the derived category of Y and then talk about derived commutative algebra objects there by using some monadic formalism, as you're saying. Then I think X to Y will be called an affine stack if X as a stack over Y is co-representable by some derived commutative algebra object coming from the derived category of Y. So
Okay.
yeah, I guess I'm not saying anything about the map from d of X to d of Y, but I guess I'm just saying that you could use such a monadic thing to define derived commutative algebra objects intrinsic to the derived category as well. And then you could define it maybe more similar to Toen as well.
Okay, I see. But so it's not necessarily true that the derived category of X being monadic over the derived category of Y implies that X is relatively affine. Or is there some kind of statement like this?
I guess I'm just not sure. So maybe it's better if I don't say it's false or something. Yeah.
Okay, yeah, sure, that's good enough. Thanks.
Thank you, Lucas. Any more questions, anybody? If not, let's thank Shubhodip once again.
Yeah, thank you very much.
So next talk will be in October.